In this lesson, we're going to take a look at galvanic cells. So if you recall, electrochemistry is where we study processes where either chemical energy is converted into electric energy or electric energy is converted into chemical energy. So in a battery, we convert chemical to electric energy, and I'm not sure if you guys saw this set up in class back in about February or March. So it wouldn't have been colored because what we had in here was water. And by plugging in some wires that were attached to both of these into an electrical outlet, we were actually able to separate water into hydrogen and oxygen gas, which would have been what was left in the tubes over there. So if you recall with redox reactions, which we had talked about, we looked at some single displacement reactions, did a total ionic equation and then a net ionic equation. And we saw that there was a movement of electrons in these. So given this single displacement reaction, so zinc and copper sulfate becoming copper and zinc sulfate, we're going to write the balanced half reactions, state which reactant is being oxidized and which one's being reduced, and then identify the oxidizing and reducing agents. So balanced half reaction, so the first thing we'll do is take anything that is aqueous and split it into its ions that it would dissociate into. So we have zinc, which is solid, and then sulfate, if we look up in our table on the back of the periodic table, is a 2-, but copper and sulfate come in a 1-to-1 ratio. So that means as we did our crisscross, if 2- is what sulfate is, then copper must have been a 2+. And similarly over here, we have a 1-to-1 ratio, but we know sulfate is a 2-, so that means that zinc must also be a 2+. So I have zinc solid plus copper ion, Cu2+, plus sulfate ions become solid copper, zinc ions, and sulfate ions. And then sulfate ions were on both, so they were spectator ions. So overall, we had zinc solid and copper ions becoming copper solid and zinc ions. So the two half reactions then are zinc becoming zinc ions. And to balance this, I have a neutral charge over here, positive charge over here, and the thing I'm going to balance with is electrons. So if I have positive over here, negatives as well on this side will help me to get to a neutral charge. So I have a charge of 2+ over here, which means I'm going to add 2 electrons to balance this. And then the other half reaction is copper ions becoming copper solid. So here I have an atom, which is neutrally charged, ion, which has a charge of 2+. So once again, this is the side that the negative electrons will come on to end up with a neutral charge overall in the reactant side, so that I have the same charge before and after. So I have a 2+ charge, which means once again I need 2 electrons to balance the charge out there. So those are the two half reactions. Part B asks for what is being oxidized and what is being reduced. So I have two reactants, the zinc solid and the copper ion. So if you recall, we have Leoger, which can help us remember what is oxidation and what is reduction. So zinc is starting off as an atom, and then it is losing 2 electrons to become a zinc ion. So a zinc atom is splitting into a zinc ion and 2 electrons, which leave. So these are being lost. So Leo, loss of electrons, is oxidation. So the thing that is being oxidized is the solid zinc. And then that would leave the copper ion to be what is reduced, but just to check, is it gaining electrons? So the GR was gain of electrons is reduction. So copper ion gains 2 electrons, those come together to make a copper atom. So copper ions are reduced. Oops. Okay, and then the last thing was identifying oxidizing and reducing agent. So this is flipped from what is getting oxidized and what is getting reduced. So zinc gets oxidized, it loses electrons. By losing electrons, it is allowing something else to get reduced. So zinc is the reducing agent, and still the same thing, the reactant, so solid zinc. And then copper ions are the oxidizing agent, because by gaining electrons, they are being reduced, but they are allowing zinc to undergo oxidation by gaining those electrons. Okay, so we saw this in the last lesson where zinc is placed into a solution of copper sulfate. And so the different things that happen when we do that is a reddish brown deposit is going to form over top of the zinc. Now this doesn't look reddish brown here in this photograph, but there would be copper ions from the copper sulfate that would come over here to deposit on the zinc strip there. And then zinc from the strip is then going to be replacing the copper in solution. So the color of the solution comes from the copper ions. So as the copper ions are leaving the solution and depositing on the zinc, then that blue color is going to fade. And then there's also going to be energy released as heat. So we're going to get into what is a galvanic cell now. And that is one where we have redox reactions converting chemical energy into electrical. Electrolytic cells do the reverse. They convert electrical energy into chemical energy. So if we take a look at the reaction we were just looking at, so the solid zinc and the copper ions, if we place those into what is called a galvanic cell, then they can actually produce electricity. So the only way to do that is to keep the reactants from actually coming in contact with one another. So we're going to create what are called 2 different cells and have the 2 different reactants separated. So here I have 2 separate beakers. So I have copper sulfate in here and a copper strip. This is called an electrode. And then there's a zinc strip, also called an electrode, in a solution of zinc sulfate. Both of these are attached to wires, and then there is a voltmeter. So a voltmeter only measures the voltage or the difference in potential between the 2 electrodes. So there's not electricity being added through a power source. There's not a battery. That would happen in an electrolytic cell. Here, this is just measuring how much or what voltage there is between those. And then there's also a tube here called a salt bridge, and we'll get into that in the next diagram. So over here, what is happening is we'll look momentarily to determine which direction electrons flow in. So over here right now, what we can see is electrons are flowing from zinc over to copper. So what happens is zinc is going to release 2 electrons along the wires, and those are going to travel over to the copper. So a zinc atom that is making up that electrode is going to split into 2 electrons, and then it's going to become an ion. So it's going to move away from this electrode and move into solution as an ion. So it's no longer a solid zinc, it is a zinc ion. On the other side, as electrons are coming over to this electrode, We have copper sulfate solution, which, remember, copper sulfate is aqueous, and so it is going to dissociate into copper ions and sulfate ions. And so those copper ions from solution, because they're positively charged, are going to be attracted to the negatively charged copper electrode because of those electrons coming in. And as that copper ion comes in contact with the electrode, it's going to pick up 2 electrons and become a copper atom. So we have copper ions gaining 2 electrons to become solid copper. That was aqueous. And then the reverse was happening on this side. So zinc atoms, we're splitting into zinc ions, which we're moving into solution, and then 2 electrons, which are moving around the wire over to the copper electrode. So what happens here then is, in the zinc sulfate solution, there's zinc and sulfate ions from the zinc sulfate originally, but then from this electrode, we also have more zinc ions coming into this solution, which is making this solution overall positive. And then on the other side, from our copper and our sulfate ions, copper is moving over to the electrode, picking up 2 electrons and becoming a copper atom and becoming a part of this electrode, leaving more sulfate ions in this solution. So that makes that negative overall. So that's where this salt bridge that connects these 2 cells comes into play. So at the bottom of the salt bridge, there is some material that keeps the solutions from mixing. So the zinc sulfate won't come up into here. This is potassium chloride in here. That's not going to come through into there. And then same thing on this end. But what can move through is the different ions. So there is potassium and chlorine ions. So it's a salt bridge. It's aqueous as well, which means it also dissociates. So over here, this solution has become more positive because of the extra zinc ions coming into it. And this solution has become negative because of the copper ions leaving it. So what's going to happen is potassium chloride is K plus and Cl minus. So the negative ion, which is chlorine, is going to move towards the more positively charged solution to help neutralize that. And the positively charged potassium is going to move towards this solution, which has become more negative, to help neutralize that. So we have our half reactions going on at either side. And then we have our overall net reaction. Now, one of the ways that we end up showing this is called cell notation. And we tend to start with what is being oxidized. And so in this case, that is zinc. So oxidation is a loss of electrons. Zinc is what is losing electrons to become zinc ions. So I start with zinc, which is being oxidized. And then this line is to show the difference between the 2 states of zinc. So zinc starts as a solid and ends up as an aqueous ion. Oops. And then I have 2 lines, and that represents the salt bridge, which separates the 2 half reactions that are going on. And then on the right-hand side, I'm going to write the reduction. So here I start with copper ions, which are aqueous. Whoops, I keep doing that. And then that phase separation, the 1 line, so copper ions become copper solid or copper atoms. Okay, so let's take a look at an example of how we do this. And actually, one thing that I forgot to mention, so we have 2 electrodes, one where oxidation is happening and one where reduction is happening. And the electrodes actually have specific names. So similar to ions, when one is positively charged and one is negatively charged, we have different names. So ion is anything that is charged, which can be a gain or loss of electrons. Anions are negatively charged ions, and cations are positively charged ions. So similarly, we have names for our two different electrodes. So the anode is where oxidation happens, and the cathode is where reduction happens. And one of the things that we can use to help us remember that is an ox and red cat. So reduction happens at the cathode, and at the anode is oxidation. So the other thing is at the anode, because an atom that is part of the anode is splitting into electrons which are leaving and then ions which are moving into solution, the anode is going to reduce in mass because it is losing the zinc atoms. The copper electrode, or the cathode, on the other hand, because it is gaining electrons and then ions are coming over, picking up those electrons and becoming atoms, the cathode is going to grow or increase in mass. Okay, so sketch a galvanic cell based on the half reaction shown below. So aluminum ion picking up 3 electrons, becoming solid aluminum, and nickel ion picking up 2 electrons, becoming solid nickel. So one of those half reactions is not written correctly. These are both shown as a gain in electrons, which are reduction, and we'll see momentarily when we look at calculating the potential between the two cells that the table we look at is always written as the reduction. So we're going to need to figure out which one of these is going to be the reduction and which one is going to be the oxidation. So we're going to need to flip the one that's the oxidation for the half reaction. So we're going to figure out which is which, label the anode and cathode, then indicate where oxidation and reduction are occurring. We're going to show the direction of flow of electrons. We're going to show the direction of movement of ions in the salt bridge, and then write a balanced ionic equation for the reaction. So the first thing we'll do, we had aluminum and then nickel. So I'm just going to say this is aluminum and this is nickel. So in the back of the textbook in Appendix B on, I believe, page 748, although it's listed later on in the slides, there is a table that shows the relative strengths of oxidizing agents and reducing agents. So this is going to help us figure out which of these is the oxidation and which one is the reduction. So oxidation happens at the anode, but remember where oxidation happens, that is actually the reducing agent. So when we're looking for oxidation, we're looking for the strongest reducing agent. So I have aluminum and nickel. Aluminum is over here and nickel is over here. So aluminum is a stronger reducing agent. And then in terms of oxidizing agent, so that's where reduction would happen, I have nickel ions and aluminum ions. So nickel is the strongest oxidizing agent, nickel ions are the strongest oxidizing agent, and aluminum solid is the strongest reducing agent. Now, once again, oxidizing agent means reduction. So the nickel ion, so that is where we're going to have reduction happening. And red cat, so reduction happens at the cathode. And then the strongest reducing agent is solid aluminum. Reducing agent is the thing that gets oxidized. So I have oxidation on this side and anox, so the anode is where oxidation occurs. Okay, and whoops, I'll just get rid of these markings. Okay. So the next thing that we are going to do, so let's just quickly take a look. So we've labeled the anode and the cathode and indicated where oxidation and reduction are occurring. So now we need to show the direction of flow of electrons and then ions and write a balanced ionic equation. So oxidation is a loss of electrons, which means the aluminum electrode or the anode is going to be where I start with the solid, and that's going to get smaller because it is going to lose electrons. So this is going to split into ions and electrons. So that means my direction of electron flow is from the aluminum anode to the nickel cathode. So that was C, which shows the electron flow. So what happens at the cathode then is electrons are coming in. That means that I have a solution here that has nickel in it. So nickel ions are going to come over to the cathode, pick up electrons, and then create nickel atoms, making the cathode increase in mass. So I have nickel ions and 2 electrons becoming nickel solid. So this is actually the last step of the half reactions for what is happening. And here I have aluminum ions going into solution. So there is some sort of solution in here on the oxidation side where the anode is in that half cell. We have to have something that has aluminum. We can just use aluminum sulfate. And then nickel, we can use nickel sulfate. So on this side, I have positive aluminum ions, negative sulfate ions. Those are balanced in terms of charge, but then I keep having aluminum ions coming into solution every time I have 3 electrons leaving from one aluminum atom. 1 aluminum ion comes into solution. Another 3 electrons leave, another aluminum ion comes into solution. So overall, this side is getting more positive in terms of the solution, whereas here I have electrons coming in. The positive nickel ions are coming over to here, combining with those electrons, picking up the electrons, becoming nickel atoms. And so here I'm losing positives, so I have more negatively charged sulfate. So for my salt bridge, I can use KCl. So if I have more positives on this side, potassium is positive, chlorine is negative, so that means my chlorine is going to come over to this side and potassium is going to come over to this side. So I need to show my ion movement, whether it's with an arrow or just by drawing the correct ion over here. So I can also up here, instead of having written KCl, I could have written Cl minus on this side with an arrow and K plus on this side with an arrow to show that ion movement. So I have my electron movement, so flowing from my anode to my cathode. Because of the charges of the solution, I have negative ions from my salt bridge coming towards the solution on the anode side, and the positive ions from the salt bridge coming over to neutralize the solution on the cathode side. And then I have the half reactions, which show what is happening at each of those electrodes. Okay, last thing is standard cell potentials. So this is just the difference in the potential energy at the anode and the cathode. So that's the electrical potential of the cell. And we can measure that in volts. Page 748 lists the standard half cell potentials for reduction. And the list is given in order that whatever is most easily reduced is at the top. So you can also use that list to decide what is going to be the reduction and what is going to be the oxidation. So the table there gives relative values, and it's based on a standard hydrogen electrode that has a standard potential of 0 volts, and then that's used as a reference to assign potentials to all of the other half cells. The electricity that gets produced by the cell is equal to the difference of the standard reduction potentials of the reduction and the oxidation, so the anode and the cathode. So we'll take a look at those and an example question of how to calculate that. So in a galvanic cell, we are always going to move from the thing that is most likely to get reduced to the thing that is most likely to get oxidized. If we want the reverse to happen, we would have to give electrical energy to the system, and that is called an electrolytic cell. So a galvanic cell is spontaneous. So we're always looking at the thing that is more likely to pick up electrons. And if you remember in grade 11, we talked about in the back of the periodic table, there was the list of the activity series of what is most likely to displace something else. And so this is the exact same thing. We're just looking at it in terms of a different context. So the first thing that we will do to calculate the cell potential is find the reduction potential of the two different substances, compare the electrodes, and decide what one's the anode. So the oxidation is what's lower on the list, and the cathode, or the reduction, is going to be what's higher on the list. And once again, this is for galvanic. That is the spontaneous reaction, and if we wanted the reverse, we would need to actually apply electrical energy. So we're going to write the half reactions, and the reduction is written as that in the table. The oxidation is given as the reverse reaction because everything is written in terms of a reduction. And then the calculation is the standard cell potential is equal to the reduction potential of the cathode minus the reduction potential of the anode. So because we are subtracting in the formula, we don't need to convert the reduction potential to an oxidation. So there's another version of the formula where we would add, but in that case, we take the value of the reduction potential and we multiply it by -1. So we would flip the sign because the reaction would be flipped. So the way that we have this formula, because of the subtraction, we don't have to do anything other than just take those values right from the table. So this is what the table looks like in the back of the textbook. And I've screenshotted just the couple that I need for the example question we worked through. So calculate the standard potential for the galvanic cell in which the following reaction occurs. So 2 iodine ions and bromine become iodine and 2 bromine ions. And then predict whether the reaction will proceed spontaneously. So the first thing we need to do is our half reactions and then get the reduction potentials from the table. So there's the reduction potentials. So I start with aqueous iodine and end up with I2. And if I look over here, this is actually the reverse reaction to that. And it is also lower in the table. So this is written as the reduction. Because it's lower in the table, it's actually going to be the oxidation, and so that is flipped from what we have here. So the half reaction is I2 plus 2 electrons becomes 2 iodine ions. And then I have liquid bromine becoming bromine ions. So I have a neutral over here, and I have a 2- charge here. So I need to add electrons onto this side. So a neutral and 2 negatives makes overall a 2-, and here I have 2-. So we see the electrons going on the opposite side, two examples we have done before, but that was because we had a neutral on one side and a positive on the other. This time we have a neutral and a negative. So bromine plus 2 electrons becomes 2 bromine ions. And I just copied right from, the list there for before. So this should be written reverse because we started with the iodine. And that will combine together and then lose 2 electrons. Okay, so we have the reduction. Is that because it's higher up in the table, it has a larger value. So as we look over here, and this one will then be the oxidation. So that's the anode, and this one is the cathode. So we have, this is the E of the cathode, and then that's the standard reduction potential of the anode. So to calculate the reduction potential of the cell, we have the reduction potential of the cathode minus the reduction potential of the anode. So 1.07 volts minus 0.54 volts, and that gives us 0.53 volts. And the way that I determine if this is going to proceed spontaneously is if the standard potential of the cell is a positive value, then that is a galvanic cell and it is spontaneous. If it has a negative value, then it would be an electrolytic cell, and so it's not spontaneous. You would need to apply electrical energy in order for that to happen in that direction. So here we started with iodine ions becoming iodine solid. So I'm writing that in that direction, which that is flipped from here, which is the anode then, which is where oxidation happens. And then the higher one is always the cathode, where reduction happens. So that is for a galvanic cell. So if the thing that is higher matches with the half reaction that you would get from here, then it's going to be spontaneous. But then the other way you can tell is by the positive value in your standard potential. So some practice questions. This is from the new textbook, page 641, numbers 1 to 10. So this is really 2 different questions that go through labeling the 2 half cells. So that first type of question we did where you had the 2 beakers, labeling what's anode, what's cathode, where's oxidation, where's reduction, what's the direction of electron flow, what's the direction of ion flow, and writing the half reactions. So the questions 1 to 5 are doing each of those parts for one question, and 6 to 10 for another. And then page 647 is looking at the example we just did, which is the calculating the standard potential for the cell and then determining whether it is a spontaneous reaction or not. And at the end of the slideshows are all of the questions and answers to them as well, if anyone has handed in their textbook already.